Dear students, this is our second class on lithium-ion battery. In the last class, we covered up to LiCOO2 and its structure, intercalation, and deintercalation of lithium. Some of you have some doubts in the last lectures. I am trying to clarify those at the start of this lecture. So, one of you asked me how to depict one-on-one plane. So you go one unit along the z-axis, one unit along x and y-axis, and connect those points. You get a triangular plane. Here I am missing one atom. So these 6 atoms which are here will form the 1 1 1 plane. I can find a plane which is parallel to this. That is one unit along z here, and one unit along x, and one unit along this y direction. So that forms this 1 1 1 plane, which is actually parallel to this plane which is here. Okay, these are all two parallel 1 1 1 planes. Since these corner atoms are involved in making the 1 1 1 plane, so we will have another 1 1 1 plane which is parallel to this here, and the fourth one here. And some of you had a doubt how to view this crystal unit cell from the z-axis, z direction. So here I have labeled the atoms. These 4 atoms, if you view through this direction, z direction, these 4 atoms will eclipse these 4 atoms which are at the bottom plane. So what you would see is only atoms 1, 2, 3 and 4. So how do you depict this in a 2D? So what we have done, if I call this as a zeroth plane and call this as first plane, then the atoms which are at the zeroth plane, I put a circle and denote it as 0. The atoms at 1 unit away in the z direction, I denote it with number 1. If you have any atom in between these two, then I will put another circle, I call it as a half. And some of you had a problem in understanding this notation. So I can divide this unit cell into 8 small cubical, and you can see at the body center of each of those cubes you have the tetrahedral voids, and those tetrahedral voids are in this direction is 1/4 away, and from the bottom it is 3/4 away, and then those tetrahedral voids which are here is 1/4 away from the bottom in the z direction. So that's why I have written them as 1/4 3/4 1/4 3/4 when you look from the z direction. This is how it looks. And see this Mgl2O4, it has got 4 oxide ions. So if this is making CCP array, then there will be 4 octahedral sites and 8 tetrahedral sites. Since you have only 2 aluminum 3 plus ion, that will occupy one half of the tetrahedral site, that means 2 sites. And since we have only one Mg ion, so it can occupy only 1/8 of the available tetrahedral sites. So that may be either in the T plus site or T minus sites. So it actually alternates. So in the 1 mg, 0.5 mg goes to T plus site and 0.5 goes to T minus. And this is where we stopped in the last class. So this LiCOO2, it's a material which is available in the discharge form. So if you make a battery with this material as cathode material and lithium intercalated graphite as the anode material, then first you need to charge the cell. When you charge, lithium will be stripped away from this lattice, so it's called deintercalation, and then gets intercalated in the graphite. So if you imagine, if you strip the entire lithium that is available, then you will have a layer of COO6 octahedra which are edge shared, and again there is a gap, and there is a layer of COO6 octahedra, and there is a gap, a layer of COO6 octahedra, and so on. But that structure is not stable. So you, in order to keep this structure stable, you have to leave certain amount of lithium in the lattice, otherwise it will transform into another lattice which is irreversible. That means it won't come back to LiCOO2 lattice when you try to intercalate lithium. And we can also look at it in a different way. So this is a layer of, say, cobalt. This is another layer of cobalt. In between you have lithium. So if you strip, so this cube will be separated from this cube. So that's kind of a layered material is what you get, layered compound. And this is another angle in which I have shown the 1 1 1 planes, how they are parallel to each other. I can see this. This is a cadmium iodide structure wherein I have a layer, which is this circle which is shaded, and then there's a B layer which is an open circle, and that forms the octahedral cavity here, that is the small circle. So the cadmium 2 plus will be accommodated in this octahedral cavity. Remember, there are two iodide ion, that means it will form two octahedral cavity. Only one of them is occupied by the cadmium 2 plus. Where is the next one? Next one you can visualize. If I try to put the C layer in CCPRA, the C layer will be here. Okay, here and here and here. That means these sites will transform into an octahedral site, but that will be slightly above these octahedral sites. Okay, one layer above. But since those sites are vacant, so this there is no connection between this AB layer and the next AB layer. So there is a gap. So that is a van der Waals force is acting in these gaps. So this is a CdI2 layered material. Imagine if I replace cadmium 2 plus with titanium 4 plus, the iodide minus plus S2 minus sulfide, then you get a TiS2 structure, which is same as, which will look qualitatively same as CdI2 structure, which is a layered structure. But TiS2 can be is a material available in the discharged in the charged form. So when you make a battery with a TiS2, so first you have to discharge the battery, because then only lithium will get intercalated into the TiS2 structure, layered structure. Each time when a lithium goes in, you will have one titanium going from 4 plus to 3 plus. So this is another view wherein I have shown the layer of TiS2. So these triangle holes are actually the tetrahedral holes, where it is empty currently because they are not occupied. Only cadmium, which is inside this polyhedra, that means that is octahedrally coordinated. So this completes the discussion on the lithium ion battery. Now I am going to introduce material for a zinc ion battery. Imagine we have octahedras, right? Metal O6 octahedras. If they are connected like this, that means two octahedras are edge shared, and these two corner share with the other two octahedras. So it will form a 2 by 2 lattice, and this cross section area is about 2.5 into 10 power minus 8 in case of alpha MnO2. So that is sufficient for the zinc 2 plus and intercalation and de-intercalation. Now in the next slide I will only take this segment, and you can see these colored dots are the Mn4 plus, and these quadrilateral is a represent the octahedra. So when you intercalate one zinc into this, it brings two electron along with it. That means two Mn4 plus site will go to Mn3 plus. This is how zinc get intercalated into alpha MnO2. And there are many types of MnO2, many polymorphs: alpha MnO2, lambda MnO2, beta MnO2, and gamma MnO2. And you can see the way the octahedras are connected here. In this case, octahedras keep changing its orientation. This is a 2 by 1 structure. And here I have compared the cyclic voltammogram, which shows the zinc deintercalation and the zinc intercalation chemistry. In this case, I used zinc 2 plus as the reference and counter electrode. That means it is just a battery wherein zinc anode is present and your cathode material, which is alpha MnO2. So when you measure the potential at which intercalation happens, that means let us first look at the zinc intercalation. The potential at which zinc intercalation happens, that means zinc entering into this tunnel, right? So that happens around 1.3 volt. The potential at which zinc deintercalation happens is around 1.7 volt. There is about 0.4 volt difference between the charging and discharge, which we call it as polarization. So polarization is very significant here, which is related to the energy loss that happens due to zinc intercalation and de-intercalation. But this curve, the same CV in case of beta MnO2 shows there is no zinc intercalation at all. There is no, because the area under the peak is very insignificant. Similarly, if you take gamma MnO2, it is intercalating, but there are problems. The intercalation happens in two separate events. In one case, MnO2 goes to Mn3 plus, and then Mn3 plus goes to Mn2 plus, and it is looks like a reversible cyclic voltammogram. That means we may able to intercalate the zinc, but we may able to extract only very little of it. So you can compare the area under this curve, these two curves, versus the area under this small curve. Only a fraction of what which we have intercalated is available for deintercalation. So this is not a good cathode material for a zinc ion battery. So delta MnO2, although we can successfully intercalate and deintercalate, but the voltage separation is very high. So the polarization is very high. So it is not really yeah, interesting material for the battery application. However, you can bring down this gap doing certain tricks. For example, you can dope the manganese site with some other transition metal, such that the energy involved in intercalation deintercalations or difference in energy involved in intercalation and deintercalation are smaller. Or you can introduce defects at the oxygen site. So I can make M1O2 minus delta. By that way, we can also manipulate this energy difference. So if you introduce a defect in the oxygen lattice, so the Coulombic force between the zinc ion which is diffusing through this channel and the surrounding oxide ions in this tunnel will be minimized. Thereby, we can store more zinc and retrieve it successfully. Okay, and also the energy gap between these two peaks, or the potential gap between these two peaks, will come down. Actually, people indeed have tried that. So these are all various oxide materials and phosphate, vanadium phosphate materials which are suitable for the zinc ion intercalation and deintercalation. You can find more information about these materials in these references that I have given. And as I said, zinc ion battery is interesting in comparison to lithium ion battery, because zinc ion battery operates with an aqueous electrolyte. So aqueous electrolyte is inherently safer. In case of lithium ion battery, we use a non-aqueous electrolyte, so which faces the thermal runaway problem. That means if the battery gets excessively heated up, there is a chance that electrolyte might catch fire. And also, if zinc ion battery accidentally opened, or if you use zinc ion battery in a car or something, and if there is a collision, the battery breaks open, then when it contacts moisture or air, there's a chance of explosion, but such things are not possible in case of a zinc ion battery. So in those safety aspects, chicken butt is really good. In addition to that, India has about 10 million metric tons of zinc reserve. So making a technology which is based on the raw materials available in India would give energy security to our energy economy. Okay. So as I said, if I want to reduce the Coulombic interaction between the zinc 2 plus and oxide minus ion, you can introduce some kind of oxygen deficiency in the lattice, and then you can improve that. So that was done in this paper, and they have showed about 400 milliampere hour per gram of capacity, and demonstrated 2000 cycles of charge discharge. So more information you can find in this paper. So if you have any doubt, you please write an email to me. And also, our next class will be on the next Monday at 11 a.m. Good evening.